Okay, so as I said, k-anonymity is still to this day quite useful notion. People use it in many cases. The law never requires it officially, but as much as the law's language can be mapped to formal definitions, k-anonymity is somewhat more naturally mapped to it. And it definitely has the appeal of some very interpretable guarantee. The K means something very clear. Right? Whatever it is that you learn about me, you cannot really tell me from a whole bunch of other people.
Is it useful or is it used?
Both. It is used.
Is it useful? That's the question.
So, depending on the context, but when you think about it, being masked by a whole bunch of other people is, in a way, what we think of when we say privacy. And when you think of all the counter examples that people will give, when people will show something and say, this is privacy violation, typically it cannot even meet like 2 anonymity. So it's hard to find a natural example where someone has 5 anonymity and yet the release feels like really unprivate. Yes, we saw examples, but it's like, not that hard. But perhaps the most problematic aspect of k-anonymity is that it doesn't compose. What does that mean? So, had there been a single data release in the entire history of humankind, we could have thought of a whole bunch of things that you can do that, will say, well, this data release will not be sufficient to cause too much harm. But the thing is, the world is complex, and many things happen. So we release something, and then people can match it to something else, and someone else releases something, and then we can combine them, etc. So one family out of many families of attack, called composition attacks, where you say there is a data set, and there were multiple private releases of information based on this data set, and then someone takes these several private releases, combines them, and reaches, and the combined data is less private than each of the different releases, which is still, that's okay, that makes sense, right? If every release leaks some information, then combined they leak more information. But if the degradation in your privacy can be arbitrarily large, then we're in trouble. Right? If I would know something like, let's say it's linear. Let's say if I have 2 releases that are 10 anonymous, so combined they're only 5 anonymous. Okay, fair enough. So I would know how many releases I'm planning to do, what is my target K, and then I say, well, if I want 5 anonymity after 4 releases, so I'll have 20 anonymity per release. Maybe it's hard to achieve, but at least I know what happens. Danger is that sometimes things can break completely. That large anonymity becomes like 0 anonymity. So here we would have one example, and in many ways this feels like sort of a Sudoku problem. So I'll start by just mapping this example to the definition. So remember, we have identifiers, quasi-identifiers, and sensitive information. So in this example, what will be the identifier? ID. What will be the quasi-identifiers? Sex, married, and employed. And what will be the sensitive? Disability. This is not a objective statement, but for our purposes. Okay. So this is the setting. I will keep carrying the yellow column just so we would remember who is who, but it will be, the numbers will be sort of grayish to remember that we don't really release them. Okay? So here's an idea. I would release 3 separate data sets. Each one just removed one of the columns. Okay? So the leftmost data set is a data set where so far I didn't change any row. I didn't compress anything. I just removed one of the columns. This is basically a data set that allows people to predict what is the probability that you will be disabled given your sex and marital status. And the second one is the probability of your disability given sex and what is it, and your employment status, and etc. Okay, fair enough. What is the K? For what K is each of these data sets K anonymized? Well, I reorganize them. So you see the numbers. This is why I have the numbers, in case you can identify them to remember who's who. And it turns out all three of them are 2 anonymous. Right? So basically, each of this is 8 rows, and it was exactly 2 by 2 by 2 options. So removing one got me to have 2 columns. 2 elements that are identical for any 2 columns. Right? This is my release. And the question is, so basically this is what I actually released. Yes, this is what we know, and this is what I actually released. And the question is, given that I released all 3 of them, what level of anonymity remains? And so each one of them to anonymity, and the question is what happens when it ends. Does anyone have an idea how can we attack this this release? Sorry?
Some of the data is out there in the open already.
Why?
Well, because, yeah, they're too anonymous. They're too anonymous, but they both have the same secret information, so...
Exactly. So to be formal, what you're saying basically is that the sensitive data is also a quasi-identifier. This is effectively what happens. So if I want to identify a row, I have another hint besides the fact that its sex is, let's say, 0 and its marital status is 0. I also know something about its disability. And now I can start playing with it. So here's an example. Now I completely remove the values, and we will try to figure it out ourselves. So can you propose, maybe I'll give one example and then we'll try to do the rest. So here's a fact. If I know these 2 values, any of these 2 values, that does not tell me necessarily anything about the sensitive one because this is too anonymous. But in the other direction, it might have a one-to-one correspondence. So if you look at the left table, there's only a single row with 0 in disability and 0 in marital status. And for that row, we have sex equal 1. Okay? So now, this is a rule we can carry over to other places. So what other table we have where we have both disability and marital status, but we don't know the sex? Well, here we don't have the marital status, so it's this one. Well, let's look for a row that has 0 and 0. It's this one. So basically now we can fill a 1 here. Okay, and now all we need is to find, so now we know everything about this row. So now we need to find it here, and we're done. So one of the rows we fully reconstructed. Okay, so take a few moments and try to do the rest. This is like literally a Sudoku kind of game.
They're taking the pictures of,
all right.
yeah, so that I can actually start doing it.
So let's try to do it together. Who can give me one row that they managed to reconstruct?
Take the top two over there. You take
Wait,
the top two
wait.
on the left.
Which table we're starting with?
We start with the top two on the left.
Okay.
So we see that
Top
six-
row?
Yeah.
Okay.
The top two rows, which are equivalent. So
Okay.
sex equals 0, disability equals 1. We
Mm-hmm.
know that married equals 0.
Mm-hmm.
So let's look at one of the other tables where we have, we look in the middle table, sex
Mhm.
0, disability 1.
So we have this row.
We
then
know that
has-
married must equal 0.
Yes. Okay. We know that the marker needs to work, but it doesn't. Okay,
And then-
and where's the other? You should have another row. Here, it's this one. This is also 0. Now, well,
just
first we
copy
can
the
go
rows.
back.
Um,
We know this is 0 and this is 0.
And in the right table, we also know we gotta
There's a
find
1,
0, 0, 1
0,
and 1.
1, 0, 0. What is it?
1, 0,
Here,
0.
it's this one. Oh,
Well, then
wait. No, now I'm worried. No, it's
No,
a
1,
1,
0,
0, 0.
1, 0, 0, 1.
Yeah.
Where is it? What am I missing?
Wait a second. No,
Am I
oh,
missing
no, oh, in the middle one you use the.
Oh, no, right. Is it, oh, okay. I used the wrong. Yeah. I filled the wrong line. Right. So
And
where
then
was
you see a
it?
0 and a 1.
Yeah.
It's the third row.
It's a third.
Third.
Okay.
Yeah.
So it's 1.
Oh, yeah.
Okay. This is what makes sense. Here there's a 0, 0. Sorry, 1 and a 0
sex
and a
and
0,
in
6.
disability.
Yes.
A
so-
0 in sex and a 1 in disability.
Yes. So this is this one, it's this one, and then it's this one. So now we know that here it's a 0 and a 1. So now we have here a 1, 0, 0, 0, and a, which
0,
is
0, 1, 1.
this one, and where's this one? It's this one. Okay. Other rows.
On the right, on the right table, if you both disability and unemployed, you are not married.
1 and 1. You are not married. This is the only one? Yes. Okay. So, disability and employment. Disability and employment, it's this one. Oh, right. Disability and employment. So this one is also not married. And since this is this one, so now we can put here 1. And now let's look them up. This is a 0, 0, and a 1. We already had it. This is a 1, 0, and a 1, 1. And we have the 0, 0, and the 1, 1. No, wait, that one we had. Sorry, this is 0, 0, 0, 1, and yeah. Okay, we have all three. Next,
0 in sex and 0 disability has a 1 in married.
where are you looking?
The second set, the second pair,
Mhm.
in the left one, 0 in sex and 0 disability has a 1 in married.
0 and 6 and 0 in disability has a 1 in married? Oh, you're looking here.
Yes.
0 and 0 has a 1. Always.
To be honest,
Right.
at this
Okay.
point, we only look
So
at-
0 and 0 has a 1.
Because we only look at the leading 0. We don't even look
0,
at the second
0
zero.
has a 1.
We only look at the 0. We don't even look at the second 0.
Oh, right. Now that we already filtered more. Yes. So now we know this one is a 0, 1, 0, 0, which is this one. And this one is 0, 1, 1, 0, which is this one. And now we put it here. This is a 0, 0, 1. You have it here. This is a 0. And you have a, which one is the newest
0,
one
0,
that I
1,
added?
1. 0, 0, 1, 1.
0, 0, 1, 1 is the new one.
So 0, 1, 1, we put a 0 at the lead.
No, this one is not the new one, I think. I think
Uh,
it's this one. It's a 0, 1, 1, 0. You just did.
oh yeah.
Okay, and finally, what will we do? We have
Well, we put
this one doesn't predict anything, but this one predicts. 1 and a 0 predicts a 1 in the remaining one, and 0 and a 1. Oh, actually,
We could
the
also-
remaining one have to be 1. So we have already a 1 here, and now we
Those are also
have
one. We have ones in the middle.
1 in both of them.
Yeah. Because,
Okay.
there are ones in both of them in the left.
And now this one is 0 and 1 is 1. Okay? So it's not the most exciting Sudoku in the world, but it took us a bunch of minutes and we're done. And indeed, let's see if we got it right. No, we. Oh no! Yeah, no, it's we need to compare these two. This is what we needed to do. 1 0 1 0 1 0 0 1. I mean, these two are flipped, but it's okay. All right. Good. So, we saw how to do this simple attack, and
By the way, Moshe, I noticed the previous one, they weren't actually in the right order.
they weren't.
No.
Oh, okay. I deleted. We won't spend the time again. But yeah, could be definitely that
You might wanna-
we got confused
you
in
might wanna
what.
look at the slides.
Oh, it was not
Yeah,
lined
so this-
up.
Because over there, they were 1 to 8, you want them to be set up, not 1 to 8,
Okay.
the order in which they are on the right side.
Could be. Yeah, I understand. Right. Yeah, I thought I remember that I fixed that from last year.
You have to look at the slide
I
and.
don't know. Okay, I'll check. Thank you. Okay, so we had this simple attack, but actually we can do many more sophisticated ones. So I'll show just one example that I'm really impressed by because it's like, it's really evil in a way, but it's also a good reminder of how much more sophisticated everything can be. So here's the idea. When we define k-anonymity or L-diversity or whatever, there's a problem that there's no clear trade-off. So it's very easy to be more anonymous. I will just combine all of them. I will coarsen things so much that everything will become like a single value that is repeated how many times, like as many elements that I have. So when I propose an algorithm for k-anonymity, I need to have some definition of what is it that I'm trying to optimize in the other direction, the utility. So here's one common definition that people had, is they say y is minimal if you cannot refine this coarsening, so assume we don't delete, we only do coarsening. So if we cannot refine any of the categories without losing the k-anonymity definition. Meaning it's sort of it's a local minima. It's not necessarily a global minima, right? Because could be I could have completely changed things such that on one hand I will have more categories or more refined values and yet remain k-anonymity, but at least it means that now there is no change I can make. That any refinement that I can propose must break k-anonymity. Okay, and this is a relatively natural requirement. It is especially useful because it turns out that finding the optimal k-anonymous representation for various definitions of optimal is like an NP-hard problem, right? Because you can imagine it's sort of an integer programming kind of thing. You won't get out, you won't get away very easily. But showing that it's locally optimal, that's very easy. So like greedy algorithms will already do that. So this attack by Aloni Cohen from like I think a few years ago did the following tricky thing. They said, if I got a k-anonymous data set and I know that it was produced by an algorithm that tries to be minimal, well, now I have another hint. besides the information that I got and the Sudoku that I can start playing, I also know that I could not refine it. So what does it mean? That, for example, if you have 3 values that are all the same in the way I see them, and all I wanted is to be, what is it? So this is 3 anonymized. Let's see, what was it? Why is this? No, this is 2 anonymized, I think. Never mind.
3.
Why? Here you have only.
Well, X is the raw data.
Oh, sorry. Yeah. Y and Z, right? X is the data. Y and Z are the anonymized versions. All right. So I have these 2. I know they are 3 anonymized, and by the fact that they are 3 anonymized, I know that I couldn't have sort of refined any of them and maintain that guarantee. That is another hint. And by adding that into the optimization, he managed to reconstruct data sets even that were like much more problematic than the simple example that we gave. So this very specific attack is unique to k-anonymity, but when you sort of zoom out, what you can take out of this idea is the fact that if I know your algorithm, that is also helpful in my attack. Right? If I kept my randomness or my swapping or coarsening or whatever it is that I do secret, maybe then it's hard to figure out, well, how did we get to this data set? But since we can't guarantee that the way the data was constructed is necessarily kept private, once people know what it did, once people know what you're optimizing for, or what are you trying to do, or what rules you are following, I can say, oh, you do these kind of things, you can only do that, you must do that. Therefore, I have more information when I'm trying to reconstruct. Okay, so let's do now 2 things. One is let's try to scale up the Sudoku example that we had in order to have a better idea of how can it work in the real world, which is exactly what happens in the class assignment. And second, we'll have just an example that can give us a taste of what happens when we really use powerful tools. Okay, so here's the question. Let's say I have now a large data set. To be formal, it's a multi-set. Everything that we call here is a multi-set because elements may appear more than once. That's the whole point. So formally, everything is a multi-set, but I will keep calling it data set from time to time because intuitive. So I have a multi-set with m features. And they're all considered quasi-identifiers. And then the other one is the sensitive information. Okay, so, and for simplicity, let's assume they're even binary. Okay? So, and the setting now is just, well, if I have k columns of quasi-anonymizers, well, quasi-identifiers, then I can drop each one of them. So I have m tables that I can release. And let's say for each one of them, we also made sure they're k-anonymous. So in the previous example, I didn't have to do anything else besides just dropping one column because I chose a data set such that once we dropped a column, we already got 2 anonymity for free. But in the general case, this is not the case. Have some data set with n elements. It has m quasi-identifiers, so it has m subsets that we release, or full data sets, but subset feature, and each one has to be k-anonymized for some k, so it was coarsened in some way. And now I want to run the same attack that we mentioned before on this release. So let's start with a simple example, as we always do in computer science. Let's not think about efficiency, just what can we do? Is there an algorithm that can solve it?
It is an NP. Do you have similar to SAT, where like what assignment fulfills all of these?
And who said there is such an assignment?
Well, there was an original data set.
Exactly. So the fact that there is an original data set from which these n data sets were constructed means that there is at least one assignment of values to these n by m matrix. I'm sorry, n by m plus 1 matrix that satisfies all the anonymized matrices that we use. But of course, that is exponential. And indeed, in the general case, this is a NP-hard problem. But we can do something that gets relatively close. Typically, I would not go into any formal claims about the utility of this example, but we will see that in practice it's very, very accurate and very efficient. So here's the idea. Step 1, let's create the superset. Step 2, let's create the subset. This is the general idea. What do I mean by that? For any data set, Si, which corresponds to having all the elements with one missing feature and maybe some coarsening, I can create a extended subset, which is all possible assignments. What do I mean by that? If I have something that is like, let's say, 1, 0, I don't care what does it correspond to, right? Let's say star corresponds to, I can't tell you. Maybe this one is a star because this is the column that was dropped, and this one is a star because the k-anonymity algorithm decided that it must not tell me, and this is the sensitive bit that is 0. Okay, I have that. Well, what rows correspond to this one? Well, 1 0 1 1 0 1 0 0 1 0, etc. Right? 4 options. So I take this row and I create 4 possible rows that might be assigned to this one. And this way I do it for every row in this matrix. I create all of the copies, all of the rows that could correspond to this. Okay? And I do it for all elements. So now each subset that started as n elements blew up to like a very large number. Right? But some number. Okay. Then I can look at all of these values, all of these rows, and I can ask how many times do they appear in each of these data sets. So, one step before, I combine all of them, and let's start with that. This data set that combines all of the rows that I got from all of the data sets, by definition, contains the correct data set. Is that because, again, each one of the expansions, is the real value, so it's contained in all of them. But furthermore, I can sort of concatenate all of them.
Intersect.
Sorry?
Intersect?
Yeah, sorry, intersect all of them. Now, let's be formal. What does it mean to intersect here? These are multi-sets. So intersection means that not only that I check which element should remain, but also how many times it should remain. So if an element appears here once and here twice and here twice, so it remains only one copy that remains. But if it appears, let's say, 2 and 3 and 2, so you keep 2 copies of it. Okay? So up to the fact that intersection in multisets is a bit weirder, I can say even that, right? So I intersect all of these extended data sets, and I still know that this intersection definitely includes all the elements that are in the real data set, maybe more. And then what I do is I filter. So I won't go into all details of how I filter here, because this is somewhat convoluted and also not going to be in the assignment, but here's the general idea. Now that I have a large data set, that I know some of the rows here were in the real data set and some were not. Now I can start moving from the other direction. I can say, look, for each of the privatized rows, I need to find a corresponding row in the real rows that explains it. Which one is it? And some of them will have an example, and some of them won't, right? So, for example, if I have here the 1, 0, star, 0, okay? And I'm looking for explanations here. So if I have 1, 0, 1, 1, 0, and also 1, 0, 1, 0, 0, then I don't know which one of them is the real one. But if the only one that had a 1 and a 0 and a 0 was the top one, and this one, let's say, had a 1 here, then I know that this one has to be in the data set. Why does it have to be in the data set? Because I have this row in one of the privatized data sets, and it has to correspond to some real row, and if this is the only one, if the only candidate, then I know this one is in the data set. So once I did that, I added this to the data set that I am sure, that the reconstructed one, and I can cross this one out. And then you can repeat it, and gradually start adding rows that must be there. So when you think about it, what we did in these two stages is, by 2 stages I mean 1 and 2 I treat them as one stage, and 3 is the second stage. So basically, when you think about it, what happened is, step 1, I created a superset. The S prime that I had here, this one, the concatenation of all of them, sorry? The intersection, right. Is definitely, it definitely contains the real data, all of the rows in the real data set. And the second step only contain rows that belong to the data set. So now I can, how can I use it? Well, that depends on the type of attack you want to do. So typically what people would like to do is to say, here's a subset of elements. Well, maybe I didn't reconstruct all of the elements, but here's a bunch of elements that I can say for sure were in the data set. So if you release S double prime, you have no false positives in a way, but you might have false negatives. You might have missed some of the elements. If you release S prime, you have no false negatives, false positives, but you have some false negatives. But
Has false positives, no false negatives.
So okay, it's a matter of terminology. What do you define as positive? If positive is you were in the data set, so this one S prime has false positive and not false negatives, and S double prime has false negatives but not false positives. Yeah. And this is very easily implementable, and this is what we'll do in the class assignment. So why did I show this if I don't have any formal claim about it? Because basically what happens is that if I worry about my privacy, I don't worry that someone will prove that they can attack me. I worry that someone will just attack me. It doesn't matter if we have, like, the rules of the game are rigged against the privacy preserving crowd. If we want to guarantee, if we want to make someone relaxed enough or trusting enough to give me their data, I need to prove something. But if I need to cause harm, all I need to do is to cause the harm. I don't need to write any proof for that. So here's an algorithm I cannot, variants of it we can reason about, but it doesn't matter for our purpose. Here's an algorithm, I can write it, it runs in 5 seconds on your notebook, and it reconstructs data sets of hundreds of rows and dozens of columns with no problem. So this is really practical. And if it's practical, it's a problem, even if we can prove, and even if in some cases we won't be able to reconstruct, or in some cases we'll have a mistake. Why? Because as long as in some cases we will be able to reconstruct, this is something that you should worry about. So here's an example from, again, jumping back. This one was classical, old style, old computer science terms, like 20, 30 years old. Notions of privacy and attacks. And here's an attack from this year. And what did they do? There's a bunch of people from Anthropic, but maybe still Google, I don't remember. Because Nicolas Scalini moved from Google to Anthropic, and I don't remember where did he work when he released it. So this is a data set that some company, I think maybe Amazon, released transcripts of interviews of candidates. Candidates were interviewed to the job. But AI took the recording and wrote the transcript, and they were released, for training purposes, etc. And they took this transcript, which, we see here a small portion of it, but the transcript was like a bunch of, like 10 minutes. It's not a very long discussion. And they didn't look at it by eye, didn't do any hard work. They just gave it to an LLM, and they said, look, there's a lot of information here. Try to extract the profile of the person. And you can see they say, I work in biology, my supervisor and I talked to, this, we did that, Well, you get some hints. So you can say, this person works in computational biology, their education is physical science, etc., etc. Search. And then you can search in LinkedIn or in people's private personal websites or anything like that. And they manage to identify them by their preprints, by their university profile, etc. Now, in that interview, the person might have also said something somewhat sensitive. They might have said they didn't like their previous employer. They might have said something about their background. And how do they do it? They give it to an LLM. Now, can we prove anything about what the LLM would be able to do? No. Do we need to prove? No. Do we need to worry? I would argue yes. So, this relatively old privacy notion, I think, is relevant to us for two reasons. One is it is a very good lesson in how careful we need to be when we propose privacy definitions, and how problematic can it be when we only rely on heuristics. And on the other hand, the types of attacks that were carried on 30 years ago and the type of attacks that are carried on today are very different in practice, but are very close in spirit. They all rely on the same insight that we can piece together many, many small pieces of information, and the combined result is a much larger harm. If someone takes a picture in the street, we don't consider it a violation of privacy because, the street is a public theme. But if someone will piece together all of the pictures from all of the security cameras in the city, they can basically track wherever you've been throughout the day. And that really feels like a privacy violation. So this is what we should have in mind when we're trying to come up with a better privacy notion that can protect us against people piecing together many things. Okay, so the remaining 3-4 minutes, I will just discuss what is happening in this course. So, this is an applied DP course, so question 1 is why have a course about privacy? Why is it an interesting thing? And I would argue for a bunch of reasons. One is privacy requires us to move back and forth between a formal definition and some intuitive notion, because again, we care about it not for some abstract notion, but for something that is in the real world. It is a very modern field, and it's growing, so thinking about it is like being in the forefront of science. It is implemented, which is a big deal, because one of the challenges in some of the theoretical fields is like, well, it remains in theory. So you can do complexity theory, and all you care about is, if it's polynomial or exponential, but then you started working in the industry, and all they care about is that, the constants of the time it takes you to run the code, not the time it takes the code to run necessarily. So here we're in a world where writing a better proof translates to a better a privacy product in a way. And generally speaking, I would claim that having this sense of paranoia is a good idea in this day and age. And of course, it's fun, in my opinion. Why applied? That's another question. So here's the main motivation of this course, in my opinion. It somehow combines my experience as a physics student in my undergrad and as a manager in a high-tech company. People learn by doing more in some way, but definitely a different type of understanding. Again, a different type of understanding than just by solving some theoretical questions. So in physics, it can be that with all due respect to what you learn in the theoretical mechanics course, once you ran some experiments in the lab, you got a different and typically deeper type of understanding. You would go to the industry and you would be asked to implement something that is exactly what you learned in 5 courses, and yet you will make a ton of mistakes originally until you figure out, oh, this is what matters really. And effectively, this is also what happens when you do research. So I think this is a very good opportunity. And combining the two, basically, and this is the important thing to clarify, this is an applied course, not a programming course. So yes, we will program somewhat throughout the course, but this is not the end, this is the mean. Programming is a way to do something with our hands, and that something will help us understand. But what the thing we're trying to understand is still the core theoretical notions. So the structure, give or take, will be the first 4 weeks will be attacks, privacy attacks, and in the definition. So as you saw in this lecture, and the next one will be the same, is we'll be sort of moving back and forth until we will conclude in a way what is the notion that we're moving forward with. Is like so here's my proposal of what privacy is. Well, here's the way it can break. Okay, so now that I know how things can break, maybe I could come up with a different proposal, and then we'll do this back and forth until we will settle on something. Spoiler, it's going to be differential privacy. And then we will have 2 sessions, one on privacy-preserving mechanisms. So there are like these building blocks, but it turns out that how you put together the building blocks can be very significant, and it can shave sometimes constants and sometimes even asymptotics from the basic private toolkit. And then we will move on to private machine learning and put together the attacks and the improved protections. And what we will gain by this is 2 things. One is, well, this is what people do these days. Like the most common private algorithm run these days is DPSGD, the private variant of how we train neural networks. But even more interesting is we will see something that I'm gonna give some hints throughout the course to it, but like once we'll get to the machine learning part, it will become very apparent that overfitting and privacy have a lot to do with each other. Intuitively speaking, both of them mean that the hypothesis that the model is tailored a bit too much to the elements in the training set. And by understanding the relation, we will hopefully better understand both of them. And then we'll have a few advanced topics, some of them related to synthetic data set, and some of them related to like the more modern results that we have in the context of machine learning and other definitions. Okay, so they said this is going to be a fun course. We will be going back and forth between discussing theoretical notions and applying them. This time it's going to be it was like a board exercise. Some of them will be with code, and we will see how easy it is to define privacy. We'll see how easy it is to break it.